Yeah. Okay. All right.
Yeah, so we'll take
It's on?
minutes for
Yeah.
people to trickle in.
All right, yeah, sure. Perfect.
So we have an atomic clock here, precise atomic clock from this.
Oh, wow. Oh, awesome. All right. Thanks a lot. Oh, does this work? No.
Okay, maybe we should begin. This clock tells us to start. It's my pleasure to introduce and welcome Scott Aaronson, who's visiting us from Austin. Scott started his computer science career as a 15-year-old undergrad at Cornell. He then did his PhD at Berkeley. From there, he moved on to Waterloo, and IAS, then Waterloo, and then MIT. So he's moved around, and then ended up in Austin, Texas, where he holds a chaired position, Schlumberger chaired position. He's a winner of many awards. One notable one is the Waterman Award. He's an authority on quantum information and quantum computing, and he's also quite well known for his popularization of quantum information and quantum computing, and also for his pretty witty and cool blog on Substack that I read.
Not yet Substack, but maybe it'll switch. But you know.
Okay. Obviously, you don't really read that often.
Well.
Anyway, so with that, please join me in welcoming Scott.
All right. Well, thank you so much, Leo, for the kind introduction. Actually, it's funny because I have not announced anyone, but I am talking to Substack about maybe moving my blog there, but I haven't done it yet. So it can join like all the my blog is one of the last holdouts right now to not be on Substack. But okay, but thank you. It is always great to be here in Boulder. Actually, I was supposed to give this colloquium in March of 2020. You can guess what happened. This was my first trip to be canceled because of COVID, and I believe that this is actually the first in-person department colloquium that I'm giving since COVID. So it's great to be back out. So I want to talk about how much information is in a quantum state, and this talk is going to cover a lot of ground from like basically 20 years worth of theorems that sort of I and others have proved to try to address this question, and then it's going to lead up to something that we just posted on the Quant PH archive last night. Okay, so it's just so. Yeah, so I am at UT Austin. I'm actually formally I'm on leave this year to work at OpenAI in San Francisco, but this talk will have nothing to do with AI, except that I did ask DALL-E how much information is in a quantum state, and that was its artistic rendering of the answer to that question. I don't know if there's any insight there. Okay, but my starting point is going to be, a simple fact, which was, maybe the starting point for all of quantum computation, which was the observation that Richard Feynman made, in his lecture 40 years ago that really started the field. If you have an entangled state of n particles, then just to keep track of, what is its state, quantum mechanics since 1926 has unequivocally told us that nature has to maintain a vector of exponential in n complex numbers. Okay, so if we think of them as two-state like let's say spin 1/2 particles, or as we call them qubits, then 2 to the n complex numbers, right? So our state is a unit vector in c to the 2 to the n. We would typically write it like this, a sum over all possible n-bit strings x of ket x times some amplitude alpha sub x. Okay, now this is an absolutely staggering amount of information for nature to be keeping track of, right? We're saying just to keep track of 1,000 measly particles, there is some scratch paper that we don't see, right, where nature is writing down 2 to the 1,000th complex numbers, which is more than the number of particles in the observable universe. Okay, and every time something happens, there's a unitary transformation or whatever, nature is crossing off all of those 2 to the 1,000 numbers and replacing them by new numbers. Okay, now of course we never actually see these numbers. That's kind of a problem. Okay, but we need them to calculate the probabilities of the things that we do see. So in a certain sense, we have to say that they're there. Okay, and this exponentiality, like if it doesn't trouble you, then it should. Right? No, this is, I have to advance the slides this way. To a computer scientist, this is arguably the central fact about quantum mechanics, this exponentiality. Even though, for generations, I think it was not the main fact about quantum mechanics that people dwelled on. But, this is the thing that makes quantum mechanics, as far as we know, intractable to simulate using a conventional computer, right? Thereby motivating the goal of building a quantum computer. Okay, so let me just give you a couple examples of where this exponentiality rears its head. Okay, I mean, of course, it does do so all over physics. One example would be for the task of quantum state tomography. Okay, which just means you have some machine that every time you press a button, it spits out a system in a particular quantum state. Let's say it's a mixed state, okay, or something. It could be a row, whatever. And so you can get as many copies of it as you want. You can measure each copy in a different basis. Now your goal is you would like to learn what is the state. Like let's say learn it as a matrix. You could say for a very trivial reason, this task requires exponentially many copies of the state. Okay, like if it's actually if you want to learn an n-qubit mixed state, then the number of measurements you need grows like 4 to the n power. Okay, why? Well, just because that is the number of parameters that there are in the density matrix, right? And this is not just a theoretical problem. This is a practical problem. When people try to learn what quantum state they are dealing with, like if you had a prior idea of what your state is supposed to be, then you can do much more efficient things, right? But if you don't know if the state could be anything, and now you want to determine what it is, then yeah, you need a number of measurements that scales exponentially. I think it's been done, maybe with about 10 or 12 particles so far, full quantum state tomography. But even just to do it with 8 particles, this was an experiment from Innsbruck. They needed like 656,000 different measurement settings. Okay, I don't know how much grad student labor that translated into. Okay, but you can see that this doesn't scale. Okay, now another thing that sort of motivated me for much of the I guess 25 years now that I've been in quantum computing has been the skeptics, okay? The people who believe that quantum computing is all a bunch of bunk. Okay, now, now of course it is, if they just say that, the applications of quantum computing to machine learning and finance and optimization have been grossly exaggerated and overhyped, and and building a quantum computer will be much harder than many people think it will be, and maybe the money will run out, and a lot of people are doing this for the wrong reasons. Then I say, okay, I guess I'm a skeptic too then, okay? I agree with all of that, okay? But then there are the people who go further than that, okay? And they say, we believe that quantum computing, or they say quantum computing is clearly impossible, okay? It is just, everyone who's working on it just making an obvious error, right? They're just not, seeing that nature must prohibit this for a fundamental reason. Okay, and then, what I've always said is, as soon as you say that, then the ball is in your court, right? Now, you are the one who has to explain, what is it that breaks down in our conventional understanding of physics, right? That will, that would explain why quantum computing is not possible. Okay, like for quantum computing to be possible, in some sense, is the boring possibility, right? It's the conservative possibility. It's just if everything works like the textbooks say. Okay, for it not to work, you need some alternative description of the world that would somehow avoid this exponentiality that that seems to be inherent when we describe things as unit vectors in a Hilbert space. So so I've shown here some few famous computer scientists and physicists who are adamant that quantum computing is not possible, for some of them, I think what it, some of them, they kind of like, enumerate, okay, here are assumptions that are made in quantum error correction that might not be fully justified, and blah, blah, blah. Okay, but then the trouble is, like, if you say, well, here's a new error correction scheme that addresses that, then they just, unblinking, they just switch to a different objection, right? Which shows that none of that stuff about error correction was ever their real objection in the first place, okay? And so what is their real objection, right? And it seems to be something like, well, it's just too extravagant, okay, for nature to be manipulating an exponential amount of information, this exponentially large vector of amplitudes using only a polynomial amount of work. Right? It sounds like a free lunch. It sounds like a perpetual motion machine. Okay? It sounds like the sort of thing that shouldn't be possible, right? And like, when people, as physicists, you all know that when people propose their latest design for a perpetual motion machine or for a superluminal telephone, right? I mean, it's like it might be very complicated to delve into the details and explain what's wrong, but something is wrong, right? And and so they're saying, quantum computing ought to be like that. Right, and okay, but so one objection is just to say, well, quantum mechanics is here, just suck it up, right? But let's say to actually build the quantum computer, which I mean that might be ultimately the only way to answer the skepticism is with the actual device. I'm sure some of the skeptics won't be convinced even then, by the way. But there's a different, maybe less obvious response to the skeptics, which is to say, well, let's actually be careful. Like, in what sense is it really an exponential amount of information, right? Maybe that's just an artifact of our sort of bad, way of thinking about it, right? That we are sort of imposing our, classical ways of thinking on something that's fundamentally different, right? Maybe if we thought about it in the right way, it wouldn't look like an exponential amount of information. Okay, so that's kind of the starting point for this talk. Okay, that when you ask, I'm sorry, this says how many qubits. It should be how many bits. Let me just. There we go. Okay, there we go. Yeah, and asking how many bits we need, or how many bits are really there in our entangled system of n qubits. We have to be ridiculously careful in how we phrase our question operationally. What are we actually asking? Okay, and if you don't believe that, then I hope that I'm going to give enough examples in this talk to drive home this point. Okay, so here's an analogy. Okay, even classically, okay, if I just have a bunch of n classical bits, right, and I don't know what state they're in, I could describe my knowledge using a probability distribution over the set of n-bit strings. Okay, that probability distribution is already a vector of 2 to the n, in this case, non-negative real numbers. Okay, but so you might say that already in classical computing, there is this exponentiality that just to keep track of n bits, I need 2 to the n parameters. Okay, but no one really loses sleep over that. Right? Because they say, look, a probability distribution is something in our heads, right? It's not out there in the world. It's just a mental bookkeeping device. And anytime I choose to, I can just go and look at the bits. And when I look at them, I'm going to see that each one is either definitely 0 or definitely 1. And so in that sense, there were only n bits all along. It was just that my ignorance of those n bits took 2 to the n parameters to describe. Okay, and now something it's clear that at least something somewhat analogous to that is true with qubits, right? Like when I measure n qubits, I just see n bits of information, right? If I measure each qubit, say in the 0 or 1 basis, right? I force each qubit to decide whether it wants to be a 0 or a 1. And then, whichever choice it makes, it sticks with it, right? Okay, but now you might wonder, is there some very clever way that I could nevertheless take way more than n bits and sort of stuff them into a state of n qubits in such a way that I could reliably read them out later? Okay, so that's now that is a good operational question, and that's exactly the one that Holevo studied half a century ago. Okay, and he proved this famous theorem, which says that if Alice sends an n-qubit quantum state to Bob, and then Bob measures that state, then Bob can learn at most n classical bits that Alice knew that she wanted to transmit to him. Okay, that's assuming that they had no prior entanglement. If they did have prior entanglement, then the number doubles to 2n bits. Okay, because of super dense coding, right? But it merely doubles, right? So yeah, okay. There's maybe this factor of 2, right? But basically, n qubits are behaving like n classical bits, or at most like 2n classical bits. Okay, for the purpose of channel capacity, for the purpose of how many qubits do I need to send this number of bits across a channel. Okay, so a running theme in a lot of my work over the last 20 years has been to show how for many other purposes, besides just channel capacity, there is less information in n qubits than meets the eye, in the sense that we can actually give classical descriptions of n qubit quantum states that will need only a polynomial in n number of classical bits. and that won't be good for all purposes, but that will be good for many, many purposes, right? That will get us surprisingly far in letting us predict and calculate the behavior of that quantum state under, a wide variety of measurements. Okay, so I had something called the post-selected learning theorem in 2004. I had this quantum pack learning theorem in 2006 or 7, and then I had work with Andy Drucker, my then student, where we improved that. And then I came up with this thing called shadow tomography, like 5 years ago. And then online learning of quantum states, which was with all of these authors. And then we connected shadow tomography to differential privacy a few years ago. So I'm gonna, have like one or two slides each about each of those things. Okay, and in some sense, what is underlying all of them is the linearity of quantum mechanics, right? If the Schrodinger equation were nonlinear, then it would actually be true that you could just take an n-qubit state and just sort of treat it as if it was a memory, storing 2 to the n complex numbers, and then you could, pick which one you wanted and read it out, right? It would be as if you could stuff 2 to the n information into n qubits. Okay, but because quantum mechanics is linear, right, there's this severe restriction on how much you can get out when you make a measurement. And we see that principle just sort of again and again and again. So let me just start with what I like to think of as the absent-minded advisor problem. Okay, I became aware of this problem when I was the student, right? And now I'm the absent-minded advisor, I guess. But the idea is, an advisor, wants to be super helpful, right? Obviously, right? Wants to give their students the information that they need to solve their problems. Okay, but the advisor doesn't really remember what problem each student is working on, okay? And so really what the advisor wants to do is just dole out the same advice to all students. Just repeat the same thing to everyone and let each student just adapt that advice to their particular situation, And so now here is our question, okay? Let's say that, the students could have an enormous number of possible questions, right? Their questions are, described by n-bit strings, let's say. So there's 2 to the n possible questions that a student could have, right? Of course, the advisor knows the answer to all of them. Right, that's why they're an advisor, right? But and for simplicity, we're going to say that the answers are all yes or no. We like to do that in computer science. If you have not, we will talk later about non-binary answers. But for now, let's say the answers are all yes or no. Okay, so now the question is, can the advisor just, clearly, this is a quantum advisor, okay? So, they can give their student a quantum state, that's fine. It could have n qubits. Maybe it even has n squared or n cubed, some polynomial in n, let's say number of qubits. And now each student, each student only needs to know the answer to their one question, remember, right? But now can each student take this state, measure it in some basis, depending on their question, and learn the answer to their question only. Okay? It's fine if that measurement destroys the state and they can't then use it for anything else. Okay, we're totally okay with that. Okay, so now notice that this question is not answered by Holevo's theorem, right? Because we're asking for something weaker, right? We just need a state where you can read the answer to any one question of your choice out of the 2 to the n. Okay, nevertheless, one of the early fundamental results in quantum information due to Ambayanis, Nayak, Tashma, and Vazirani from 1999 says that the answer is still no. Okay, that in fact, qubits don't really give any advantage to speak of over classical bits for this problem. Like if you want to provide the answers to 2 to the n different questions, you'll basically have to provide on the order of 2 to the n qubits, right? Just list all the possible answers. Okay, and why? Well, intuitively, the advisor could, of course, provide a superposition state that would just encode each answer as in some component of the superposition. Okay, but now the trouble is, well, what good is that state to a student? A student now has to take the state and measure it, right? And when they measure it, what they'll see if they just measure in the standard basis will just be the answer to a random question, right? The chance that it's the answer to their question will be exponentially small, right? They don't get to choose which branch comes up. The Buhrman rule chooses that. Right? And so, you might hope that you could be more clever somehow, and this theorem says, no, actually, there's no way to be more clever. Okay, so now the first thing that I want to tell you about in this talk is, it occurred to me, I guess, in 2004 or so, that this Bar-Yossef et al. Theorem is kind of a lemon, right? It's saying, sorry, there's no nice quantum encoding here. There's no quantum benefit for this absent-minded advisor problem. Okay, but very, very often in computer science, what we do is we make lemons into lemonade. Okay, all right, I don't know. Is this? I mean, however you want the lighting to be. Yeah, that's fine. Okay, so we take limitations and we turn them into positive results. Okay, algorithms, protocols that depend on those limitations. So here is an example. Okay, let's say that Alice, has some d-dimensional quantum state, say it's a mixed state rho, and she would like to describe the state to Bob. Okay, so Alice knows what rho is. She just knows it explicitly as a matrix, and she wants to tell Bob about it. Okay, the trouble is, she doesn't have a quantum channel, so she can't send Bob qubits. She also, let's say D is enormous, right? D might be exponentially large, right? So she doesn't have enough time to send rho to Bob, as an explicit matrix. Okay, but here's the good news. Okay, there is a list of yes or no measurements that encompasses everything Bob might possibly be interested in. Okay, we're going to call that E1 up to EM. Okay, so as a good example, these might be all of the measurements that can be applied using small quantum circuits, for example. Okay, or all of the yes or no measurements that can be implemented, using circuits of up to some fixed number of gates. So M might, so D might be enormous, M might also be enormous. Okay, but they might be exponentially large. And now the goal is that, whichever measurement Bob cares about, whichever E sub I he cares about, he should be able to estimate trace of E sub I rho, which is the probability that the measurement E sub I applied to rho would output yes. Okay. So then here's what one can show, okay? That, there is a protocol by which Alice can do this. By sending Bob, a number of classical bits, which only grows like log of M times log of D. Okay? So even if M and D are both exponentially large, as they could be in many applications, this is still a polynomial number of classical bits. Right, and it's inverse polynomial in the precision epsilon that you want. Okay. Now that there is, you might be thinking that that's too good to be true. What's the catch? Right, so there is a catch here. Alice might need an enormous amount of computation time to figure out what this classical message is. Bob might also need an enormous amount of computation time to interpret the message. Okay, so those are two catches, actually. Okay, but if computation time is free, then you can get this, I think intuitively very surprising compression of a quantum state. Right? It doesn't let you, recover rho necessarily as a density matrix, but it lets you, simulate the behavior of rho with respect to all of these yes or no measurements, E1 up to EM. Okay, so if we think of let's say an n-qubit state, like in terms of just the list of amplitudes, of 2 to the n amplitudes, right? It seems like a quite astronomical object. Okay, but now if we think of it in terms of the shadows that it casts, on all yes or no measurements that we could perform with a circuit of size at most n squared. Now I'm saying that it shrinks down to a much, much more manageable size. Okay, there is a short summary that encodes all of those exponentially many different measurement outcomes with only a polynomial number of classical bits. Yes?
But what happens to all the rest of the information? Like, is there some observables that there's exponentially not large enough?
That's right.
Not?
Yes. Well, you could say the total number of theoretically possible yes or no observables for n qubits is actually double exponential in n, right? Because each one could take exponentially many bits to describe, right? So there's a whole double exponential enormity of possible 2 outcome measurements where I'm not necessarily going to tell you the answer, right? But for all the yes or no measurements that you can actually implement via a circuit of a reasonable size, this description will be good enough for you to calculate the answer on those. So that's the point.
Another question?
Yes.
Does this theorem tell Alice how to figure out what set of bits to send?
It does. It is constructive. Now, as I said, she will have to do computation, which is polynomial in D and and M, right? So which could be enormous numbers. Right, but if she's willing to do that, then it's completely constructive. Yes.
So another question.
Yes.
If Bob's measurement is to do the complete tomography,
Yes.
then wouldn't that be
Good question. What happens if, good, so let's see what happens if Bob wanted to do complete tomography. Well, complete tomography, if you want to recover each entry of the matrix, then in order to encode that into yes or no measurements, you're going to have to ask for measurements that are like to a precision of order 1 over d. Right? So epsilon is now like 1 over d, and then you're going to pay, so everything is consistent that way. Yeah, all right? It's not local. I said nothing about locality. No, it can be any set of m yes or no measurements, any whatsoever. I said nothing about what they have to be. Okay. All right. So how does maybe it'll help if I explain how the theorem works, and you'll see that there's nothing about locality here. Okay. So here's how it works, okay? So let's say that Bob has gotten no classical bits from Alice yet, okay? But he still wants to guess, right? I mean, look, the whole deep learning revolution of the past decade is if you don't know, just guess. Right? That's good enough for GPT, right? It's why not? Why isn't it good enough for Bob? Okay. So, but what's he going to guess? Right now, he knows nothing about Alice's state rho. So therefore, he will make the stupidest possible guess, which is what? Rho is the maximally mixed state. Okay. Well, you got to start somewhere. Okay. Now, what Alice is going to do is she is going to repeatedly help Bob to refine his guess. And how is she going to do that? She's going to just repeatedly say to him, look, Bob, here is a measurement that is in your set of M, measure, E1 up to EM, on which your current guess will give you a badly wrong prediction. Okay? And now here is the right answer for that E sub I. So now use that to update. Okay? So she repeatedly tells him a measurement in his set on which whatever is his current hypothesis will badly fail, like will lead to a prediction for trace EI rho, which is more than epsilon away from the true answer. Okay, and then what is Bob going to do given that information? Basically, he's going to he doesn't have to do this actually physically. He can do it in his head. Okay, but he's going to say, what would happen if I took my current hypothesis, call it rho sub t minus 1, And then I ran that measurement, E sub I, that Alice told me about. And then I post-selected on getting the right answer. I just, assume condition on the event that, in the rigorous version, you have to do this with multiple copies of rho. Okay, we amplify it with, assume, and then that produces a small blow up in the result. Okay, I run this amplified measurement, and I just sort of post-select the expectation value of this E sub I is approximately what Alice said it would be. Okay, now that lets me refine my previous hypothesis, rho sub t minus 1, to a new hypothesis, rho sub t. Okay, and then we basically just keep repeating that until there is no longer any measurement in Bob's set on which he outputs, a badly wrong answer. And as soon as that happens, then we're done. Yeah.
Sorry, I missed.
All right.
How you what does post-selecting mean?
Post-selecting means Bob would imagine what would happen if he applied the measurement E sub t to the current hypothesis state, rho sub t minus 1, and then makes a measurement and then conditions on getting the right answer for that measurement. So for example, if Alice said the trace of E sub t rho is 2/3, then he conditions on the event that somewhere close to 2/3 of his measurements accept, right? When he does on multiple copies of rho sub t minus 1. Okay, and then
That's an algorithm to, it's like throwing out
yeah.
some of the measurement, but how does it?
Well, it's like throwing out some of the probability mass of the maximally mixed state. Okay, our initial hypothesis is the maximally mixed state, and then we repeatedly whittle that hypothesis down, trying to converge on what is the true answer rho, right? Which we might never get there, but the point is that even if we don't, we will get to some state which is as good as rho with respect to its behavior on these m measurements. Okay?
Post-selection gives you a map from rho t minus 1 to rho t.
Yes, exactly. Yeah, exactly. And if you were doing it with the physical state, then you would have to get lucky, right? You'd have to hope that the measurement outcome is what you want, and that's no good. But Bob can just do this as a mental experiment, right? Sure. Yeah. So okay. So I don't have a slide for the formal analysis of this. Okay, but the main point in the analysis is just that you can show that Bob can be wrong at a number of times that's at most like log of d, log of the dimension of the Hilbert space. Okay, and why is that? Well, intuitively, it's because imagine that Bob had started with the right answer, right? Imagine that he didn't, but imagine that he started with rho. In his register, okay, then he would have just gone and gotten the right answer to all of on all of the measurements that Alice mentioned, right? And you can there's a technical fact that you can make by using amplification. You can make the probability of an error very small, and if you make it very small, then there's something called gentle measurement, right, where the state doesn't even get damaged much by each measurement, so you can keep reusing it. Okay, but then the maximally mixed state has this very beautiful property, right, that it can be written as just you can pick any orthonormal basis you like, right? And then it is a uniform distribution over all of the states in that basis, right? So imagine, all right, let's just for simplicity, let's say rho is a pure state, right? It's some state psi. Okay, so now imagine that it's in some giant basis with d basis vectors. And now we say, look, if I had been lucky and picked psi from the beginning, then I would have succeeded, right? With on all of these measurements. Let's say that there's t measurements, okay? So then, and let's say I'm going to succeed on each one with at least a 2/3 probability, and so then 2/3 to the t. Well, it's got to be at least the probability that I would have succeeded, if I had started with the true state, if I'd been lucky enough. Okay, because in some sense, all we're doing is we're starting with a randomly chosen state from that basis, right? And if I had been lucky and had chosen the right basis vector out of those d, then I would have succeeded, let's say, at least 90% of the time. And now I can just take this and solve it for d. Solve it for t. And I get that t is at most on the order of log of d. Okay? So like this procedure has to hold. Like I can't be wrong more than a logarithmic in d number of times, or else this inequality would be violated. Okay? So now that my original motivation for this was complexity theory. Okay, I was interested in this complexity class called BQP/qpoly. So let me decode that a little. Okay, BQP is maybe the fundamental object of study in quantum computing theory. Okay, it is bounded error quantum polynomial time, the class of all the problems that are efficiently solvable. All the decision problems that are efficiently solvable with a small error probability if you have a quantum computer. /qpoly means that you get a polynomial-sized quantum advice state. So we're going to imagine that you get some amazing initial state. Maybe it was formed in the Big Bang, and it's been sitting around ever since, and we can just go and find it somewhere. Okay, but it depends only on the size of the input. Let's say it doesn't. It's some polynomial in n number of qubits, where n is the length of the input. Might be exponentially hard to prepare for ourselves. Some crazy entangled state, but but it's the same state for all the inputs. Okay, now what we're saying is that this class is contained in post BQP/poly. Okay, so post BQP means BQP if you add the power of post selection. So of making a measurement and then just conditioning on it having a certain outcome. Okay, so that's a much more powerful complexity class, but it's still, some class that you could simulate if you had exponential time with a classical computer, let's say. And then /poly, that means with polynomial-sized classical advice. Okay, so what this theorem is saying is that quantum advice is sort of not infinitely powerful for solving decision problems. One can always take quantum advice and replace it by classical advice at the cost of using more computational power to decode what the advice is saying. Okay, and so then that answered various questions that I cared about at the time. Now, in the 2010 paper with Andy Drucker, we actually strengthened this result to say that BQP with quantum advice is contained in QMA with classical advice. So now here QMA stands for, maybe some of you might be more familiar with this one, it stands for quantum Merlin-Arthur. Okay, it's like if you've heard of NP complete problems, this is like the quantum generalization of the class NP. Famous theorem by Kitaev says that the local Hamiltonian's problem, so finding a ground state, estimating the ground state energy of a local Hamiltonian is a complete problem for QMA, characterizes the power of QMA. So it's like all problems that involve searching over the set of all quantum states on some, on n qubits. Okay, so now what we're saying here is that if you have this trusted quantum advice, this /qpoly, you can always replace it by a combination of trusted classical advice, that's the /poly, combined with untrusted quantum advice. That's the QMA. So you can get this quantum state that you don't trust, but you can verify it using the classical advice. And that's just as good as having quantum advice that you trust.
So is that
Yeah.
the base QMA is smaller than post BQP?
Yes. So QMA is contained in post BQP and is believed to be strictly contained. Yes. Right. And so actually my email address is bqpqpoly@gmail.com. I was amazed that was available. That, no one snapped it up. But, all right. So now let me give you another example of this kind of theorem. Okay. So then in 2006, I proved what I sometimes call the quantum Occam's razor theorem. Okay, that's William of Occam. That's a Gillette. So what does this one say? Okay, this one says, okay, let's say that you have some unknown entangled state on n qubits or whatever. I don't know why. I just made it into a pure state. It would also work with mixed states, but let's say that it's psi. Okay, now suppose that you just want to be able to estimate the acceptance probabilities of most yes or no measurements that are drawn from some probability distribution, mu, over possible, different yes or no measurements, okay? So now we're changing the setup. Instead of having like a list of measurements where you have to get all of them, we have a distribution over measurements, right? Which could be over doubly exponentially many, or even over a continuum of, it could even be a continuous probability measure. Okay, that's all fine. But now we say we don't have to succeed on all measurements from this distribution, just on most of them. Okay, so then what the theorem says is that here is a procedure that works for this task. Okay, you can just choose a bunch of measurements, let's say m of them, draw them independently from mu, from your distribution, and then go into your lab, and for each of those measurements that you randomly chose, estimate its acceptance probability on your state. We'll assume that you can make copies of your state to order. And then, let's say that using your classical computer, and this step might take, a lot of time, a lot of computation time, but let's say, you find any hypothesis state, okay, that approximately agrees with the answers that you got on each of those m sample measurements. Okay, then the theorem says that, then with overwhelming probability, that hypothesis state will generalize. Okay, in the sense that it will also approximately agree with the true state psi on most further measurements that are also drawn from mu. Okay, so this is like the in computational learning theory, this is a very well-known kind of theorem, right? They're called sample complexity theorems or generalization theorems. Okay, and this is saying that this works when your hypothesis, the thing you're trying to learn, is a quantum state. Okay, but the key part, the important part, is that the number of sample measurements is growing only linearly with the number of qubits. Okay, or logarithmically with the dimension of the Hilbert space. Okay, so once you change your goal to this sort of, I've also called it pretty good tomography, right? This just estimating the acceptance probabilities of most measurements, then you get an exponential reduction in the amount of sample data that you need compared to if you, had to do full quantum state tomography. So yeah, in computer science terms, we say quantum states are PAC learnable. PAC stands for probably approximately correct. This is just a term coined by Leslie Valiant in the 80s for this kind of thing. I should mention that just a few years ago, a group in Rome, Andrea Rochetto et al., did an experimental demonstration of this protocol for PAC learning of quantum states using optics. As with most of these experiments, the result of the experiment is that my theorem appears to be true. So. But and they were nice enough to add me as a co-author. So that was, I have an experimental paper, right? Okay, all right. So now another nice variation that you can do is called online learning of quantum states. I'll just briefly tell you about this one. So now let's let rho be an unknown d-dimensional mixed state. Okay, now suppose the following. Suppose again and again, someone hands you, a 2-outcome measurement, E, and they challenge you to estimate trace of E rho to within plus or minus epsilon. Okay, and if you fail, then they tell you, here was the right answer. Here was trace of E rho, at least approximately to within, epsilon over 2 or something. Okay, and now, you're very embarrassed each time you output a wrong guess, and you would like to minimize the number of times that you were wrong. Okay, so the theorem says that there is a strategy in which you will fail a number of times that scales only like log of d. Okay, again, log of the Hilbert space dimension, divided by epsilon squared. Okay, and the strategy, is the kind of thing that you expect by now. Like you start with the maximally mixed state, you condition on getting the right answer on each of the things that you're shown. This is like the usual thing that you do in machine learning, right? And then you use these kind of dimension arguments to show that this can fail, at most log of d times in total, right? I don't know exactly when these failures will happen, right? Like the person who's giving you the examples might be very nasty. They might just pick the same e over and over and over again, a trillion times, and then obviously, you're not learning anything about any other measurements while that's happening, right? But at least you're getting the right answer on that e. Right? And then maybe they switch to something else, and then you have no information, so you get the wrong answer. Okay, but then quickly you learn. Okay, and so this is also called a regret bound, right? We're bounding the total number of failures. Yeah.
This is similar protocol as before. You're testing row in this post-selection way.
Yep. Yeah, it is. It's very similar. All right, so now let me tell you about like the most recent one, which is shadow tomography. So now suppose that you're given a d-dimensional mixed state row along with known 2 outcome measurements, E1 up to EM, and now you want to estimate probability that EI accepts rho to within epsilon for every EI. Okay, so this is different from the pack learning, because now we actually want to get all of the measurements in this list, right? And and the post-selected learning sort of did this, but it required a sort of an omniscient Alice. Okay, it required someone who actually knew the state, right, and knew a classical description of the state and could use that. Okay, now just suppose that you're an experimentalist and you just have a bunch of rows in your lab that you can create. Like, is there a protocol by which you can now do this? Or let's phrase the question this way: how many physical copies of rho would you need in a measurement procedure to solve this problem, to tell you trace of EI rho for every EI in your finite list, right? And I was, it seemed like someone must have studied this question, but it seemed like no one did. So I started studying it, and actually it was a physicist, Steve Flamia, who invented the name for it, shadow tomography. I think physicists are much better at naming things. Computer scientists come up with names like QMA/poly. Okay, but. So what can we say about this problem? All right, well, it's clear that if I had d squared copies of rho, that would be good enough. Why? Because then I can just do ordinary quantum state tomography, right? Which was proven in 2016 to only require d squared copies of rho. That's actually a very non-trivial result. Okay, but once I know rho, then I can estimate trace of E rho for any E I want. Right? Okay, now in a completely different strategy, I could also do it if I had about m copies of rho. Right? How would I do it then? Well, I would just apply each EI to separate copies of it. Right? And and those measurements might destroy the copies. That's why I need so many. Right? So now what I'm going to ask is, what if d and m are both exponentially large? Okay, so they're both enormous. Then is there still a way to do it using only a few copies of rho? Okay, and so this is what the shadow tomography theorem says. Okay, and actually my guess had been that surely this is not possible, and I couldn't rule it out, and the reason I couldn't rule it out is that it is possible. Okay, so there is a protocol that will do this with a number of copies of rho that scales like log of m to the 4th power times log of d. And more recent work by Badescu and O'Donnell, they improved this exponent of 4 to a 2. Okay, we still don't know what the optimal answer is. Okay, I don't even know if there has to be any factor of log d there, for example. Right? Maybe you can do it with only log m. Okay, but now the key idea here is this thing called gentle measurement. Okay, so I touched on it before. But gentle measurement is this very, very fundamental principle of quantum information. Okay, and it says, suppose that you make in general, measurements of quantum states are inherently destructive, right? If I measure the plus state in the 0-1 basis, I force it to 0 or 1. That's a very destructive operation. I lose the phase information. Okay, but if I make a measurement of a state rho, and if given knowledge of rho, I could have almost perfectly predicted the outcome of that measurement, then it need damage rho by only very, very little. Okay, basically, because with high probability, rho just snaps to something very close to what it was before. And so then I can limit the damage, right? And so then if I'm making measurements whose outcome would have been predictable given knowledge of the state, then I can make many, many such measurements in sequence on the same state and do it safely, without destroying the state in the process. Okay, this is used over and over and over in quantum computing and information. This principle, okay, and so that what you have to do for shadow tomography is figure out a way to take this small number of copies of rho and measure them gently. Measure them like you need to learn trace of EI rho for every I, right? And the trouble is, sometimes it might be on the knife edge between two possibilities, between yes and no, and then your measurement is going to destroy like a copy of rho, and you can't afford to lose so many copies, right? So you have to really think about how do you do this gently. Okay, and so it involves the post-selected learning theorem that I showed you before, but then you have to combine that with something called the quantum Ore bound. I'm not sure who to credit this for because I claimed a proof of this quantum Ore bound in 2007, but my proof was wrong. But then Harrow, Lin, and Montanaro gave a correct proof in 2017. So we use that, and it basically gives you this sort of gentle way to learn. Like, is there a measurement in my set that on which my state has a certain behavior? Okay, now. In follow-up work by me and Guy Rothblum, we actually made to me, kind of amazing connection. So Guy Rothblum is an expert. He doesn't do quantum computing at all. Okay, he works in an area of classical computer science called differential privacy. Okay, which is all about like if you have a database of some sensitive medical records or something, right? And now you want to, or census data, okay, and you want to let people make queries, but in such a way that you have a statistical guarantee that you will not be revealing too much about any one individual in the database. Do they have colon cancer or whatever, right? Okay, it gives you a way to do that, typically by sort of deliberately adding a little bit of noise to the query results before you return them. Okay, and I talked about like what you do to get gentle measurements, which is often you take your ensemble of states and then you make a measurement, but you deliberately add noise to the measurement outcome in order to not collapse the wave function too much when you measure, right? And he said, this sounds similar. And I'm like, okay, it's probably just a coincidence, but let's have lunch and talk about it. Turns out there is a really tight mathematical connection between these two concepts, right? Between querying a database to not reveal too much about any individual, and querying, measuring a collection of quantum states to not learn more than you want to know about which branch of the wave function were you in, right? And so using that connection, we were able to give an improved protocol for shadow tomography, which then Badescu and O'Donnell built on further to get the result that I mentioned before. All right, and then there was yet further work by Huang, Quang, and Preskel. They gave a protocol called classical shadows, which is not as general as shadow tomography, but it doesn't. The advantage is it doesn't require gentle measurement, and therefore, it is way more amenable to experimental implementation. And so people have been excited about that the last few years. Do I have a few minutes? All right, thanks. So, having spent this whole talk telling you why there is less information in an n-qubit quantum state that meets the eye, in the final few minutes of the talk, I want to turn around and tell you why there is an exponential amount of classical information there after all. All right. Well, so this goes back to an old result in quantum computing by Bar-Yossef, Jayram, and Kerenidis from 2004, and this is in the subject called communication complexity. Okay, so now we're going to imagine, we're going to create some distributed task that Alice and Bob are trying to solve, okay, such that a quantum state will be exponentially more efficient than any possible classical state for this task. Okay, so here's the task they came up with. I don't think it's one you would have come up with right away. Okay, it's a little weird. Okay, we're going to say Alice holds an n-bit string. Now this is just my example, just to illustrate it. Say that for n different people, Alice knows whether they're male or female. Okay, Bob holds a perfect matching on the set 1 to n. So in other words, Bob knows who is dating whom. Okay, let's say that n is even, everyone is dating exactly one other person. Okay. Now Bob's task. What we want is that Alice should send Bob a short message that will let him determine for any one couple of his choice, like is that a same-sex or an opposite-sex couple. Okay, so that's the task. All right, so now the question that we're going to ask is how many bits does Alice have to send to Bob in order to let him do this with a high probability? Okay, so we can first ask about it classically. Classically, I claim that Alice has to send Bob about square root of n bits. This is necessary and sufficient. Okay, why? Well, basically, Alice can just start telling Bob the genders of like square root of n randomly chosen people. Can anyone see what will happen after about square root of n time? Yes, the birthday paradox. Yes, which is not actually a paradox, but like the same reason if you put 23 people in a room, there's a good chance that 2 share a birthday, right? Because what matters is the number of pairs. Okay, after square root of n people, there's a good chance that there will be some pair that is dating, and then Bob can solve the problem. Okay, but you can, this takes more work. You can prove that there is nothing to do more clever than that, at least not classically. Okay? Quantumly, there is a protocol where Alice only has to send Bob log of n qubits. Okay? The protocol is very simple. It's basically that Alice sends Bob this state here. Equal superposition over all integers I from 1 up to n with phases that encode the values of the bits. So then Bob takes this state, and then what does he do? He just kind of directly measures it in a way that he makes a measurement where like the possible outcomes of the measurement have the form for each edge I comma j in the matching, there's an outcome I plus j over square root of 2, and there's an outcome I minus j over square root of 2. Right? And then Bob gets one of these outcomes, and then that tells him both a pair and whether that pair was same sex or opposite sex, by just seeing what was the relative phase between I and j. Okay, so that's it. So that's an exponential separation. Now, what we very recently, this is the paper that was just appeared on the Quant PH last night with Harry Buhrman and with my amazing PhD student, William Kretschmer. We realized that this, old result has a kind of cool complexity implication, with it could have been noticed like any time in the last, 19 years and somehow wasn't. Okay, and what we say is, let's look, instead of at BQP, let's look at FBQP. Okay, what does that mean? It means now we're going to allow problems that have many possible outputs. Right, so instead of a binary answer, yes or no, the output can now be an n-bit string, let's say, and there might be many possible valid outputs, right? And the task is just to output any one of them. Okay, so the class of all problems of that kind that are solvable by a polynomial time quantum algorithm is called FBQP, and then we could combine that with quantum advice, to get FBQP/qpoly, or with classical advice to get FBQP/poly, and now we say unconditionally the quantum advice is more useful than classical advice. Okay, it is incredibly rare in complexity theory that you can just unconditionally say that one complexity class is bigger than a different class. Right? It's usually just if this is true, if that is true. Right? No, we're saying this is true. Okay, this class is bigger than that one. Okay, so that's the surprise. Okay, and you can't do that for the decision problems without solving a huge unsolved problem in complexity theory. And my post-selection theorem basically showed that. Okay, so, and the key idea here is just that we repurpose this old separation due to Bar-Yossef, Jayram, and Kerenidis. Now Alice is going to have a string of 2 to the n bits. And Bob, we need a further fact that Bob's matching can be one of a set of 2 to the n different possible matchings. And, these sets are efficiently describable. And the separation still works in that setting. Okay, and what you get is that classical advice, even randomized, would have to be at least 2 to the n over 2 bits long, whereas n qubits are enough if you have quantum advice. Okay, this has a potential application to a new form of quantum supremacy, which I'm calling quantum information supremacy.